everyone. I am Madhvi Gaur, Assistant Professor, ABES Engineering College. Today I am going to discuss about B tree, all its operations which can be performed on B tree, for example, insertion and deletion, as well as the concept of binary heaps. Let us discuss all these topics one by one. First of all, we should understand what is B tree. Basically, a B tree is a self-balancing tree data structure, in which the height of the levels of the subtrees should not be exceeded 1. It should lies in between 0, 1 and -1. That is the meaning of the self-balancing binary tree, which we have discussed earlier in the AVL tree as well. It maintains as well as store large amount of data. By using the concept of B tree, we can reduce the access time in case of searching while we want to insert a particular data item, as well as we want to delete an item, then it can reduce the access time of it. In this, a node can store more than one key value, which we have studied earlier, the binary tree or BST or AVL tree. All those binary trees have node value as a single key value. But in case of B tree, there is no restriction on this. It is totally dependent on the order of the B tree. So a node can have more than one value. Similarly, a node can have more than two children, which is totally dependent on the order of the tree. B tree is mainly suited for the storage system that can read and write relatively large blocks of data. It means the main utilization is in databases and file systems. These are the important properties related to B tree concept. First one is the root has at least two children. Okay, it means root is supposed to have minimum two children. Each node can have a maximum of m-1 keys. We should remember this. A node can have maximum m-1 keys, where this m is order of the tree. And a node should have minimum of upper bound of m/2 minus keys, where m is the order of tree. Okay, each node except the root can have maximum of m children and at least upper bound of m/2 children. We should remember these. All these are the important properties while we have to insert or delete a particular data item in case of B tree. Okay, so we have discussed the main properties of the B tree here. Now let us consider an example in which I want to enter or input any data item into a B tree. Okay, I have assumed the order of the B tree is 4. Okay, we have considered this as order 4, and these are the particular data items which needs to be added inside a B tree. As we know, a B tree, a node can have more than one value, which is totally dependent on the size of the B tree or order of it. Okay, so it can have maximum of m-1 keys, where m is the order of tree, which we have discussed in the last slide. Okay, first of all, if I want to insert one, as an element can be assigned a single value. So in the node, first one is assigned. Then insert 5, there is no problem, because as per this, it can have maximum of 4 minus 1, which is 3 keys. Okay, then insert 6. We can simply insert 6 as well. Then next item, which is 2. 2 has to be inserted here, but it will not be keep inside this B tree. Let us assume this is the representation initially. Now 2 comes here. Then we have to look forward what is the appropriate position of 2, because it follows the property of BST as well. Okay, then 2 rightmost position will be this. 2 has to be placed here. Then how we can accommodate 2 here, but we cannot insert 2 here because our node cannot have more than m-1 keys, where m is the order of the tree. So there is a need of splitting this node. We have to split the node. And for splitting the node, we have to find out the median of this tree. Okay, If I'll calculate the median of this tree, now we have to count this value as well. If I want to find out the median of this tree, that will be 4. It will be 4 divided by 2 plus 1. It will be 3. Or we can assume the value. It can be 2 or it can be 5. If I assume the value of median as 2, then it will be known as left justified tree. Then throughout the solving this problem, we have to follow this concept only. If I'm considering 5 as a splitting value, then this can also be right. Then it will be right justified. Then throughout solving this problem, we have to consider the right justified format only. Then at this point, I have considered the left justified format. That's why I have split the tree at the second position. Okay, so we have splitted the tree at the 2. Then this 2 will be here, and the splitting of remaining nodes will be like this: 1 and 5 and 6. It will be splitting like this. It means we have to calculate the median value. The median value can be considered as 2 or 5. If I am considering 2, then it will be left justified concept. If I am considering right, it is right justified. And both the options are correct. Then we have done the splitting part. 1 will be splitted here and 5, 6 as a right child. Then next new node has to be inserted, which is 8. Then we have to compare this value from 2, and 8 is greater than 2, then it will go to the right part, right child. Then the rightmost position of 8 is here. And this node can retain 3 values. So there is no problem at this time. Next, we have to insert 11. As soon as I'll insert 11 here, then again splitting has to be done. I have already conveyed to you that if I am following the concept of left justified, then throughout the solving this problem, we have to follow the left justified format. As per that, if I'll calculate the median of 5, 6, 8, 11, then it will be 6. Then 6 will be shifted or moved towards the top direction. Then 2 and 6 will be placed at the same time, and the splitting will be done like this. Okay. Then 2 and 6 will be here. Left child is 1. As soon as I'll split this part, then it will have 2 children, which is 5 and 8, 11. So it means left part 6 left child or 2's right child will be 5, and 6 right child will be 8 and 11. We can show it like this as well, and we can as well draw the straight line, which will show it as 2's right child as well as 6 left child. Next item to be inserted will be 13, that will be placed here. Then 18 position will be here. Then again splitting will be done. Splitting will be done from the 11. It will be shifted here. It will have 2, 6 and 11. Here it will be 1. Here it will be 5. The splitting will be done like this, which is 8. And here it will be 13 and 18. Okay. Next item is 20. We can see here. As soon as 20 will come, then it will be inserted here, because the right child was having only 13 and 18 value. And the next value to be inserted is 20. So this node can contain 3 values. Then 7 needs to be inserted. Then it will come here like this. Then insert 9. 9 will be placed here, just like this. So this was the insertion concept in case of B tree. Okay. Now we have to discuss about the B tree deletion. If I want to delete a particular data item from a B tree, then how we can do this? So this is the B tree which I have considered for the example, and for certain data elements will be removed from this. Okay. First of all, I will delete 95. So we have to remember a node can have at most m minus 1 key and minimum of m by 2 minus 1 keys. This is for minimum number of keys, and this will be for the maximum, where m is the order of tree. Order of tree. Okay. Here m value is given as 5. So our node can have 5 by 2 minus 1, which is 2.5. Okay, upper bound we have to consider, that will be 3. 3 minus 1, it will be give 2. So it means a node should have at least 2 keys and a maximum of m minus n, which is 4 keys. Okay, minimum is 2 and maximum is 4. Fine. Okay, first of all, we have to delete 95. So it will be deleted from here without affecting the node's value, because a node can have minimum of 2 values. So 95 can be erased directly. So the node value will have 90 and 100. Next deleted value will be 226. So we have to look forward whether this B tree is containing 226 or not, which is here. If I explicitly remove this value 226 here, then a node should have minimum of 2 value. But here it will have, after deleting 226, it will have a single value. So this 226 has to be replaced with some value. So it can borrow some value either from its predecessor or from successor. So we have to see which node will have the sufficient number of values which can give borrow to this 226, so that this 226 can be deleted. So I have to look forward. This node will have 4 values. Then 300 will be shifted here, and this 226 will be erased from here. Then the node structure will be like this. 300 will be shifted here, and this 226 will be deleted. And it will be have 3 values now: 440, 550, and 601. Okay. In the next case, we have to delete this 221. If I want to delete this 221, then again this node will have 1 value only after deleting this. So it should have 2 value. Then this 300 will be shifted here, and its 440 will be shifted here. So the tree structure will be like this. It means 300 has been shifted here, and 440 from the bottom down has been shifted to the top value or to its parent value. Okay. Then we have to delete 70. We have to delete 70 here. Okay. But I can see, or I can notice, if 70 has to see or look forward that from whom it can borrow any value. It cannot borrow from here. It cannot borrow from here. But we have to mandatorily delete 70. Okay. After deleting 70, the structure will be look like this. 110. Then 70 has to be deleted. Then this 65 value will come down. Will come down after deleting this. After shifting 65, 85, 86 will remain here. And here will be 32, 44, and 65 and 81. Okay. And here it will be 90 and 100. Right part will be like this only. There will be no change. But I can see a node should have 2 values, but here is only 1. At this point in time, now 86 will look forward that from whom it can borrow the value. But there is only 1 value, which is a root value. 86 cannot borrow from here. And these nodes will be combined in case of 86. 32, 44, 65, 81. Even though this cannot contain a single value. And there is no one who can give borrow to this 86. At this situation, all these nodes will be combined. So we have to analyze this situation very carefully. At that point in time, when a particular node which needs to be deleted, or which want to take borrow from some other value, and there is no such item which can provide borrow to this item, then we have to merge all the data items to the single level. Then the tree structure will look like this. 86 will be combined with 110, 120, and 440. Left child will be 32, 44, 65, and 81. Its right child will be 86 right child, and 110 left child will be 90 and 100. 120 or 100 child will be 115 and 118. 120 right child will be 220 and 300. And 440, right child will be 550 and 601. So the main concept to be noted here is this step. This will be the final B tree, which is a height balance tree. And you can also notice the height of the tree is also reduced, through which we can reduce the access time, or for finding the searching of a particular item we can reduce the access time for that. Okay, if there is no other item from which we can borrow, then at that point in time we have to merge all these nodes, because there is no other node which can provide borrow to this 6086 or to this 70, so that there will be two nodes. But this situation was not done here. That's why we have combined or merged all these nodes. Okay. Next concept is binary heap. A binary heap is basically a complete binary tree. As in my previous video lectures, I have already explained this term. What do we mean by complete binary tree? A node, a tree structure like this, in which all the particular levels are completely filled except the last level, and the insertion at the last level has to be done from the left hand side only. In this case, this type of tree is known as complete binary tree. Okay, so basically binary heap main utilization is to efficiently retrieve the data, or we can directly retrieve the maximum or minimum element value out of that binary tree. A binary heap can be either min heap or max heap. If I want to understand the concept of min heap, the definition is the key value present at the root node must be minimum or must be small among all the keys present into the binary heap. Or we can say this root value should be less than its children. This is the min heap property. Min binary heap or min heap, again I am telling you, this root value should be smallest out of these two children. Again, if I'll talk about this node, this value should be less than both of these children, as well as this value should be less than both of these children. Okay. Next concept is max binary heap. It is just similar to the min binary heap. If I want to consider, then this root value should be greater than out of these two children. Similarly, this node value should be greater than out of these two children. This node value should be greater than its child. Let us understand this concept through one example. First of all, I'll discuss about max heap. As per the definition, if I am taking this value 20, this 20 root node value should be greater than of its children. This 20 is greater than of its children. Similarly, if I'll take some other level of this binary tree, then this 18 should be greater than out of its children. Then 19 should be greater than its children. It can be 14 and 17. So, in case of, while we will analyze this max heap property, we can say the root element will be maximum out of all the elements present. That should be first minimum, first maximum. Root element should be greater out of these elements present. This will be, it should be greater than out of these two children. They should be greater than out of these two children. And the opposite of this structure will be min heap, where our root node value should be less than its children. It should be less than from its children, from left and right child. Okay. Similarly, this two should be less than from its children. This 3 should be less than out of its children. So this is min heap property and this is max heap property. I hope you people got to know about this max heap and min heap property. Okay. Next, we can see the utilization of this concept, where we will utilize this concept. These are the applications of basically heap, binary heap. It can be done, it can be utilized in case of priority queue. It can be utilized in graph algorithms, as well as there is a heap sort concept, which we will discuss in the further videos. Okay, where we will get to know in detail about the heap concept, as well as how we are maintaining the max heap property as well as min heap property. At that point in time, we will mainly utilize the concept of heap. Okay. So this was all about binary tree from my side. This is the reference which I have referred for making this video. Thank you, everyone. Thank you, everyone, for the patience listening.